Welcome to part 4 of this series. Today, we will be building a neuron class. Let's start. So before starting with neuron class, let's define an enum that is called activation type, and that will help us keep track of the activations that we have. So I defined ReLU in the previous lecture, and we can have different types of activations. For now, I will just define ReLU and tanh. I think I did add, actually I added sigmoid to it. So let's add sigmoid instead of tanh. So let me define an activation class now. And the activation class will be responsible for applying activations to neurons. So this is the activation class, and it has static functions. And actually this should be sigmoid. And this is fine, and this should be sigmoid. So again, working with static functions. And another thing that I need to add here is an activation map. And an activation map will just help us grab that activation using this enum type as the key. So first of all, I will just add the activation for ReLU. And the second thing that I will add is the activation for sigmoid. From a workflow point of view, a user will just send this key to this map, and this function will be returned, and this activation will be applied to that value. So, and similarly, you can add other activations to this class as well. So once that is done, we are in a good spot to start building our neuron class. So let's do that. So let's try to understand the theory between neurons before coding that up. Let's assume that we have an input that size is 4. Let's say you have a huge image. In that case, the size will be 4,000 or 400,000. The size can be anything, but for this simple example, let's say that the size is 4 of our input. And a neural network is defined by a number of layers, and each layer has a number of neurons. Let's concentrate on one layer today, and this is the layer that I'm talking about, and this layer has 3 neurons. So these are the 3 neurons that we'll be coding this neuron class today. So what happens is that we need a way in which we need to transform the inputs and produce some outputs. So in this case, we will have our inputs coming here, and then the inputs will be also like this. So the inputs will be interacting with all the neurons in the layer. Let's look at the second input now. And the second input will be something like this. It will again be interacting with all the neurons. And in the end, each neuron will produce one output like this. And this process will keep on going forward and forward and forward. Each output of the neuron will have an activation function here that we just created. So an activation will be applied here. So this will be this activation function, and the user will already tell us which activation they really want. The output of these neurons will then become input of the next layer, and so on and so forth. And it will keep on going forward until we reach the last stage where the loss is calculated. So having understood that, one thing to note is the dimensions of the neuron. So a neuron is nothing but a vector of value class that we defined. So in this example, the inputs are 4. So each neuron contains a number of weights that are multiplied by the input. So here's a question for you guys. What is the dimension of the weights in each neuron that I just showed you? So the number of inputs is 4. What should be the dimension of weights in each neuron? In this example, in this particular example, the answer is 4. So each neuron should contain 1, 2, 3, and 4. 1, 2, 3, and 4. So in this case, there will be dot product of these inputs with this neuron or the weights in this neuron, and there will be an output created, and we will add a bias to that output. So there will be a bias added to it, and then we will also add an activation function, and that will be an output. So that will give us an output. So now let's code that up. As I just described, a neuron will have a vector of weights. It will also have a bias, and it will have an activation type. Let's look at the constructor of the neuron. So the constructor of neuron will take an input. We need to know how much the length of that vector of weight should be. And we also need to know the activation type that we need to. Having done that, we need to also initialize the weights. We need to give them some initial value. And here I'm just giving them a random float value. And the random float is just a uniformly distribution between -1 to 1. Once that is done, you can ignore this function for now. I just use it for testing. Once the constructor is done for neuron, we need a way to zero out all the gradients, because once the forward propagation is calculated, we need a way to refresh every gradient so that to make it ready for the next forward propagation and propagation. So we need a way to zero out all the gradients. So this is a simple function that helps us zero out all the gradients. Now, this is the main function in which we do that dot product with the input and add bias and then apply activation to it. So first of all, it takes an input as a vector and it checks if the size of that input is equal to size of the weights. If the size is not same, that means we cannot do the dot product. For dot product, the two vectors have to have the same size. We initialize a variable sum, and that sum will contain the dot product of both the vectors. So this is the main for loop in which we do multiplication. That means we're basically doing dot product, but since in C++ 17 there is no support for dot product directly, I think in C++ 20 there is, but in 17 there is not. So we need to manually do the dot product and calculate that sum. Once the sum is calculated, we can add the bias to it. And in this case, bias isn't doing much because it's always 0, but you can initialize the bias also to some other value other than 0. And there are a lot of papers on that. Once that is done, I apply that activation function. And the way I apply that activation function is I look at the activation type. And the activation type is initialized from the constructor and that the user provides. So I'm getting the activation function here, and then I'm applying that activation to that sum and then return that. And then I have some utility functions like print parameters, get parameters. It just returns the size of the parameters, which is nothing but the size of the weight plus 1 because of that bias term. And that's pretty much it. This function parameters, it returns all the parameters, which is sometimes useful, but it's just a utility function for now. So with this, we will be able to initialize neurons. And in the next lecture, we will code up the layer class, and the layer class will hold a bunch of these neurons. And a lecture after that, we will create a multi-layer perceptron that will have multiple layers. So as you can see how we started. When we started, we just created a simple value class, and that value class led us to create other classes on top of that, and soon we'll be able to run neural networks in our computers. So I hope this lecture was very useful to you guys, and I hope you learned something from it. And if this lecture was useful in any kind, I will be really grateful if you guys can please like and subscribe. And I will see you in the next lecture. Thanks.